Hi guys, Mrs. Thompson here, and today we're going to talk about Graham's Law and Dalton's Law. First one, Dalton. There's a nice picture in the corner of Dalton. It says the total pressure of a mixture of gases equals the sum of the partial pressures of the individual gases. So it's just saying if you have 3 different gases, or 2 different gases, or 10 different gases, that if you wanted to know how much pressure the total mixture of gases is, you would add up all of the gas pressures. Okay, so if you see this little picture here, it shows 2 different gases separately. Each one moving around contributes their own pressure because the collisions with those molecules and the walls of the container create its own pressure. And so you see for hydrogen, you've got 2.9 atmospheres of pressure. For helium, 7.2 atmospheres of pressure. And then if you add those 2 together in the same container, that they add up to 10.1 atmospheres of pressure. So it's just a total pressure. So we're just going to try an example. Here we go. We've got what is the total pressure of a mixture of gases, and then it gives you a list of partial pressures for 3 different gases. We're calling them A, B, and C, but they could be CO2 and hydrogen and helium. They could be any 3 gases. So I'm just going to list my givens. I have A is 2.5, B is 4.51, C is 1.2, and it is the total that I'm not sure about. Okay, since we're looking at Dalton's Law, it's P total is equal to the sum of all the gases. So there's my equation. I have gas A, B, and C. All I have to do now is plug them in. They're all in terms of atmospheres. One little tricky thing that you could get here is I could give you different units of pressure. And if I give you different units of pressure, then you have to make them all the same, because you cannot add millimeters of mercury to atmospheres. Okay. I add them all together, 8.5, 4.51, and 1.2, and I get 8.2 atmospheres. For my significant figures, I'm going to round to the least number of places, since this is addition. And so 8.2 is my final answer, since this has 1 place, that has 2, that has 1, so 1 place past the decimal is the least. The other thing that we can do with Dalton's Law, and this is something that we'll do in a lab setting, is we can collect gases and we can run them over water, and that just helps to collect the gas and to see that the gas is actually moving the water out of the way. So over here it says when a gas is collected by water displacement, the gas in the collection bottle is actually a mixture. So what happens is as that gas is going inside of whatever container we're trying to get it into, a little bit of the water itself will go into the container. Okay, so it'll be mixed in with the gas that we're trying to find. So we have to use Dalton's Law to figure out what's the actual pressure of that gas without the water. Okay, so the dry gas. All right, so it says for our first example, hydrogen gas is collected over water at this temperature. Find the pressure of the dry gas if the atmospheric pressure is 94.4 kilopascals. If the vapor pressure of water is 22.5 degrees Celsius, is 2.72 kilopascals. Let's read that. So as far as my givens go, I'm trying to find the hydrogen, so we're just going to put that as a question mark. The total pressure, so we get on here, it doesn't say total, but what it does say is atmospheric pressure. And so as that gas is collected, it will do that at the same pressure as the atmospheric pressure around it, because those pressures are going to equal. Now, if we measure the atmospheric pressure to be 94.4, that's going to be our total pressure. All right. It says the pressure of water at that temperature is 2.72 kilopascals. And so notice I have this temperature and this temperature. I don't actually need the temperature in this calculation. All I need to do is be able to use that temperature to find the pressure for water. If for some reason it isn't given to you in the question, there's a table that you can use. So you would look at the temperature, okay, and you would find either the kilopascals, millimeters of mercury, or the atmospheres. All right, so let's do this problem. Here we have, what we're going to do is P total is equal to the pressure of hydrogen plus the pressure of water. And so we know P total, and we know the pressure of water, we just have to find the pressure of hydrogen. Okay, so if I want to solve for the pressure of hydrogen, all I need to do is subtract 2.72 from both sides of the equation, and you end up with 91.7. Again, I'm rounding to places because this is addition and subtraction. And so my final answer is 91.7 kilopascals. Okay, next topic, Graham's law. And for Graham's law, before we talk about it, we're just going to go over quickly again, what is diffusion? Diffusion is just the tendency of molecules to kind of spread out through a container so that they randomly move around and eventually they're evenly distributed. We say they go from areas of high concentration to areas of low concentration, always from high to low. So if you see this container in here, they're in an area of high concentration inside of the container. Outside of the container, there aren't any of those green particles, so that's low concentration. And so the molecules, once open, or the container's open, diffuse throughout the whole room. All right, there's a lovely picture of Mr. Graham. Effusion is just gas escaping through a small opening. It's usually going into a vacuum. And so here's a picture or an animation of effusion. So the gas particles are escaping from this container into a vacuum. Okay, we need to know about how fast particles are going, and we're going to compare their relative rates of effusion and diffusion. First, we need to know that kinetic energy is determined by the temperature of the gas. So remember, that's how we measure kinetic energy, by its temperature in Kelvin. At the same temperature and kinetic energy, heavier molecules will move slower than lighter molecules. So the larger the molar mass is, the slower they're going, the smaller their velocity. And so you have this equation right here, which we don't have to worry about too much, just that it means that the heavier it is, the slower they go. You can see that in this graph here. You can see you can see their molecular speed. You can see the fraction of those molecules that are going at that molecular speed. Okay, and so what you see here is the highest peak tells me those are the highest fraction of that set of molecules moving at that speed. So we'll just look at the peaks. So hydrogen is moving the fastest at about 1800 meters per second. And then helium is moving second fastest, I guess you would say. And then as you go down, we see that they are moving slower and slower. Okay, why is hydrogen moving the fastest? That's because if we look at its molar mass, it's 2.02 grams per mole. Helium, about 4 grams per mole. Water, 18.02. Nitrogen, 28.02. So you notice as you move this direction, they're moving slower because they're getting heavier and heavier. All right, so I have some questions for you. Which gas is going to diffuse faster and why? Well, between the two, let's see, you guess first. Okay. Hopefully you said helium. Helium is going to diffuse faster because it's lighter. Okay, and I wrote that a little bit differently. I wrote same temperature, to assume that the temperature is the same. The heavier molecules are going to move slower. So helium being lighter will move faster. Okay, next question. At the same temperature, the rates of diffusion of CO and nitrogen are virtually identical. Explain. So let you do that. All right, and hopefully you looked up their molar masses. Carbon monoxide is about 28.01 grams per mole, and nitrogen about 28.02 grams per mole. So they're virtually close in molar mass, so they're virtually moving at the same rates. This could have said rates of diffusion or rates of effusion. We would treat it the same. Okay, now With Graham's law comes its own calculation, and sorry, it is a little bit more difficult than the calculation for Dalton's law. Here's what Graham said. He said the rate of diffusion of a gas is inversely related to the square root of its molar mass. And so here you see an equation that we're dealing with, and it's a comparison of two rates of gas A and gas B. Those are just two different gases. And it's equal to the square root of molar mass B over molar mass A. Be careful that you notice that on the left side of the equation, it's A over B, but on the right side of the equation, it is B over A. Okay. One hint, and you're going to have to squeeze this in somewhere, doesn't matter where. When you're working with Graham's law, if you have a choice, it is much easier to make the lighter gas A. So that would be what you would put here. All right, so let's try one. It says determine the relative rate of diffusion for krypton and bromine. Now, if this had said determine the relative rate of effusion, we would use Graham's law too. So it's either diffusion or effusion. All right, a little hint here. The way it's written, we're going to use gas A first and gas B second. So that means we would do the rate of A to the rate of B. A being krypton, because it's written first. B being bromine, because it's written second. All right, so we're going to plug that in. We're just going to make the basic equation and start plugging in numbers. So A being krypton, I put that on top, rate of Kr over Br2. So be careful about those diatomic gases. If it says bromine, don't just put Br. Bromine is Br2. Okay, get some lightning and thunder. So let's go ahead and do that. Let's start plugging stuff in. To do that, we need to look up the molar masses. I went ahead and put those up there. Okay. And so I'm going to put that's equal to, so the rate is equal to the molar mass of bromine, Br2, not just Br. So I add up two bromines and I get 159.80 grams per mole. Krypton, being a noble gas, is just Kr. So that's 83.80 grams per mole. And now all I have to do is just plug it into my calculator and then hit enter, and I get 1.381. Be careful when you're doing this. I like to square root, like there's parentheses that come in there, but add parentheses to say 159.80 divided by 83.80, or do that part first and then hit the square root of that answer. All right, so 1.381. The rates are not going to have any units, so just leave them unitless. And we're going to explain what 1.381 means. So all this means is, since it's written in this order, that krypton is diffusing faster in the way here. Krypton is diffusing faster than bromine, and it's diffusing 1.381 times faster. Any questions about why I got the significant figures I did? This one has 4, that one has 5, so there we go. All right, example 2. A molecule of oxygen gas has an average speed of 12.3 meters per second at a given temperature and pressure. What is the average speed of hydrogen molecules at these same conditions? Okay, so we use the equation. We set it up this way. We put the rate of hydrogen over the rate of oxygen. I like to put the lighter gas on top, so that's why I put H2 on the top, okay? Because hydrogen, being that it has a smaller molar mass, is going to be lighter. So that's gas A, okay? Then its molar mass, remember it's molar mass of the B on the top and A on the bottom. So that's what it would look like. So let's start plugging them in. Okay. Oh, there's our molar masses of hydrogen and oxygen. Gotta look those up. All right, so we'd say rate of hydrogen over oxygen. Let's figure out what those numbers are. So oxygen, according to the question, it says oxygen has an average speed of 12.3 meters per second. So this is coming from the question itself. Okay. Then we need the molar masses of O2. since oxygen is 16 and we have O2, that's 32 grams per mole, and hydrogen is 1.01. So we have two of them, so it's 2.02. Okay, we'll go step by step on how to solve this. Alright, so the first thing I like to do is just go ahead and take care of the right side of the equation because there's nothing but numbers there. So I'm just going to rewrite what I have on the left, and that's equal to 3.980. So I've performed the math on the right side of the equation and just rewritten what's on the left. Okay, then I want to solve for rate H2. Right now, in order to get the 12.3 out of the denominator, I'm just going to multiply both sides by 12.3. Okay, 12.3 cancels, and I get that the rate of H2 is 3.980 times 12.3. Okay. So when I perform that calculation in my calculator, round to sig figs, I get 49.0, and then the unit for the speed is always meters per second. Okay. All right, here's another one. Example 3 says an unknown gas diffuses 4.0 times faster than O2. Find its molar mass. All right, so the unknown gas is diffusing faster than the oxygen. Since the unknown gas is moving faster, it has to be lighter. So I'm going to put that gas as gas A. Okay. So that means the rate of A, I'm just writing A because it's unknown, over the rate of O2 is equal to the square root of the molar mass of O2 over the molar mass of A. Okay. So then if I fix that, here's what I'm going to do. I actually know the relative rates. It's given to me in the problem. What this is saying, the unknown gas diffuses 4 times faster, is that the relative rates, this over this, is equal to 4. So I'll put that there. Okay. So that 4 is coming from the question itself. Alright, so then we need the molar mass of oxygen, which is 32, and the molar mass of A. We don't know what gas A is, so we just put molar mass A, or you could just put X. Okay. How do we get or solve this problem? Well, we've got an X on the bottom, so what you have to do is you have to get rid of the square root sign. How do you get rid of the square root sign? You square both sides. So I'm going to square both sides. Okay. When I do that, 4 squared is 16. And then what happens on the right side of the equation is that when you square a square root, that square root symbol just disappears. So got 32 grams per mole over the molar mass. Getting late here. All right. I need to solve for molar mass of A, so I'm just going to put 16 over 1 just to help me solve this. Cross multiply. Okay. What I get is 16 times the molar mass of A is equal to 32. Solve for molar mass of A, I just divide both sides by the molar mass of A. And so that works out to be 2 grams per mole. All right. Hope the math wasn't too scary for you on that one.